Right, good afternoon, or dazzled by the bright lights. A bit about hot weather, challenges we face, particularly going forward, challenge of hotter summers. Lots of things in here, some a bit of background, a bit of theory, a bit of some of the thoughts I've had, some of the things we're looking to try and change, some of the things we're trying to do differently. So a bit of a whistle-stop tour, a bit about theory. It's only really a fairly basic thing. CWR track shall have the buckling strength to withstand the environmental and operational loads imposed upon it. Fairly simple, straightforward, not something we can always manage, and thus the result we have buckles. Risk of buckling, it's not just buckled rails and the risk of derailment. Track forces build up hot weather and cold weather and apply to a lot of other assets. So IRJ failures during hot weather closes up the joints, track circuit failures, S&C pushed out of alignment, no longer correctly operation there. We'll see a lot of track circuit and switch S&C failures during hot weather and equally during cold weather. We try and balance our stress-free temperature, but the forces are significant. So something there in adjoining switches and crossings. One of the questions earlier, why paint the plain line and not the S&C? Paint the plain line, that's the bit that pushes on the S&C. So it's not always a bad thing to limit those forces around it. So it's what's happening next to things, it's what's pushing into things that often causes the problems. High tensile forces in cold weather, increase in broken rails. We have about 2/3 of our broken rails in about 1/3 of the year. So a big impact, both sides of it. It's not just hot weather and buckling, but you've got to balance the cold weather. I won't go through it in detail. You can go and work out your tensile forces, fairly simple formulae with coefficient of expansion and a few other parameters. If you look at what that actually means, it probably swings the forces. So if you look at perhaps 30 to 35 degrees C above and below our stress-free temperature, that's going to put something like 600 kilonewtons, 60 tonnes in compression or tension into the rail. So hot weather, eventually that leads to a buckle. Cold weather though, that's quite a stress in the rail. Even defects grow quicker when they're under a lot of tension. Broken rails much more likely. Defect sizes become much smaller, critical defect sizes, so that the size of defect the rail will fail from is smaller. So it's a challenge, it's not just hot weather. A bit about stressing. You can stress at a low stress-free temperature. You then increase your risk of buckles. You can stress at the top end of it. So the bottom plot there, you can push your SFT up very high, but then in cold weather you increase the risk of defective and broken rails. At the moment in the UK, we run, as a stress-free temperature, we target at 27 degrees. There's a rough sort of compromise between what's the extremes of cold weather and the extremes of hot weather, so something like 30, 35 degrees above and below your stress-free temperature. We do that mainly by tensile, pulling the rails during colder weather to stretch them before we weld them up. Other things that can affect it, it's not just the stress-free temperature. If we have disturbed track, deficient track, that will effectively move our stress-free temperature down quite dramatically, and suddenly then you've got a much higher risk of buckling. And then in the bottom right-hand corner, you can just see we've got intervention levels we set for applying a watch person to apply a 30/60 or 20 mile an hour speed restriction. Once you reach those critical temperatures, they're based on the SFT. So if you've got something that lowers your SFT, then those trigger points effectively come in earlier. A bit about the theory of buckling. A lot of people look at this. Does it really matter? Yeah, it makes a big difference. That's what our standards are written around. There's two key temperatures. There's a TB max, the maximum temperature you calculate. Effectively, that's the temperature the track will reach with no vehicles, nothing, and it will definitely buckle at that point. The compressive forces are beyond the lateral strength of the track. It will buckle without any imposed forces. You then get a TB minimum value, which is effectively the point where there is no risk of it buckling. And the bit in the middle is where you've got dynamic loading from vehicles. So how much can you push above the TB minimum so that you're still in a safe place where the track is not likely to be pushed over the top and then buckle suddenly under a vehicle. That works well for strong track on the left-hand side. You've got a big difference between the max and min. We take a rough figure of around 50% of the energy under the curve as our limit, where we then start to apply watch person or speed restrictions. On the right-hand side, that's weak track, deficient, shortage of ballast, low SFT, a number of things there. Doesn't show this big difference, and that's why some of our standards, you'll see the difference between CRTW, CRT 30/60, CRT 20 are much smaller. We've got a much smaller window to operate in between your TB min and TB max. And in very weak track, it will effectively try and move progressively under traffic when subjected to thermal forces during hot weather. So a big difference there in your temperatures, but also how much you can manage the track and the risk. Unfortunately, it's much harder to manage the weak track than it is to manage strong track, which generally doesn't need managing. So some general challenges. It's not just hot weather. It's very rarely that the rail will buckle just because of hot weather. A whole load of things, and I won't go through them all, but your normal ones: disturbances, deficiencies, low stress-free temperature, poor fastening conditions, things like disturbing the track, work that disturbs the track, loosens the ballast. All of those, combine those with hot weather at those locations, that's where buckles are going to be a risk. A bit about how we manage it in track. Rail stress and CRT registers, essential foundations for what we do. We record this stress-free temperature. The point at which we believe the rail is stressed to is neutral, or the temperature it's neutral at. We've got to do a lot with the SFT. We cut rails, we change components, we have broken rails. All of those will have normally one effect on the stress, is to lower it unless we reinstate it carefully. So making sure we keep a register where we've disturbed that stress-free temperature or lowered it or carried out work. That goes in our rail stress database. And the second key one, our CRT register, which is effectively a record of any disturbance or deficiency, making sure we got that calculated correctly. Because if we don't have something in a CRT register, it effectively goes unmanaged during hot weather. We won't go out and just put a speed on. Most of our reaction in track is a critical rail temperature derived from whatever's in the CRT register. Foundations for hot weather management and how we push things forward. A little bit about performance. Through sort of my career in the railways, I've seemed to have looked at this quite a bit, but that sort of things have changed. And certainly some years, I remember 2003 was not a good year with 137 buckles. Last year, exceptionally hot, but 26 buckles. Perhaps you'd argue there was 27. I'm taking 2 on one site right next to each other as a single incident, but generally quite good performance in that situation. When you look at the maximum temperatures, what we thought of maximum 1976 35 was exceptional, really exceptional. 2002 40.3, that's becoming the norm. So what was exceptional in the past? So I think there is some reassurance here that things are perhaps improving. The asset is behaving better. We put heavier, stronger track forms in generally through renewals, more modern designs, certainly got a higher lateral strength and greater resistance to buckling. It's not without risk. Buckle, we've had a number of derailments over the years. That was an example at Huddlesford. We derailed a freight train in 2003. Quite a significant impact. And that was a buckled rail on the approach to a structure. It kinked in the transition zone. A number of things wrong there. Ended up with a freight train down the embankment. So it's one where, although an incident doesn't happen frequently, the more buckles we have, the greater that risk that we're going to get one that derails something. It's the wrong place at the wrong time. Another way of looking at how did we do, this is a plot of the number of buckles against the number of days over 25 degrees centigrade. 2022-23, so last year, generally we were below the line, and it's a bit of a crude line. That's a bit of a scatter to draw a single line in there, but you can see the very hot summers previously, we were generally much higher number of buckles. So I think from that point of view, there's some assurance we did quite well, but good safety. But I think anyone would ask, how did that impact performance? When you look at there, we had routes closed for the first time I can ever remember not having any trains running for a significant period of time. A lot of blanket speed restrictions, local speed restrictions, some cases freight cancelled completely. So big challenge. That was a real hit on performance, whilst perhaps you can look it's a good factor with safety. So what can we do differently? We've seen some improvements, significant reductions in the number of buckles over the previous years, certainly against some of the exceptionally hot years. We've done things in there specifically, reduced high-speed buckles on full depth timbered S&C. We artificially lowered the CRT values. We end up putting speeds on earlier, but the negative of that, we're now under a lot of pressure to run a more reliable, better performing railway during extremes of hot weather. If you look at some of the figures, we had 14 buckles in 2003 at high speed S&C. We had one last year, and I'll show a bit more on that one. Where, when and why, I won't go into a lot of detail, but typical ones there, most of them 95-pound bullhead. We had 4, 21 in 113A, one at a junction between the two, 9 buckles in S&C, or 5 within 100 metres of S&C, 12 in plain line, 6 in jointed track, 20 in CWR. You can cut and dice the data. Nothing in Sen 60, so our modern design of track, plain line Sen 60, a lot more resilient to higher temperatures. Various things there, that's just looking at the buckles by line speed. Certainly it's better to have more on the left-hand side at low speed, much fewer at the right-hand side. So some examples there, you can cut and dice the data, buckles by region, and I think some of this you start to then draw into the effects. When does it happen? 18th, 19th of July, hottest days of the year, the most buckles. But we then saw another period of quite hot weather in August, and similarly another spike in the number of buckles then, even though those were at lower temperatures than the track had seen earlier in the year. You can cut them by region. Perhaps the only example and note here, last year nothing in Scotland. So I think that's more about geographical temperatures and talking to colleagues there. If it had got to 38 degrees C in Scotland, there would have been a lot of problems. It was quite a lot lower than that. So we think of the country, it's the UK, but it behaves very differently when you compare with what's happening in South East against what happens in Scotland. We have one set of standards, one set of rules, which fits everywhere at the moment. A few examples of buckles. Swanley, buckle in the S&C. Always a risk. You've got a pushing force on the turnout road. You've got potentially a weaker track form where you've machined the foot off the rails in full depth S&C. So quite a common, not a significant buckle, but enough that that's a rough ride and not able to run at line speed. Tunbridge, whatever thought it was a good idea to put S&C on a tight curve right on top of a fixed timber structure. But we are where we are with that, and it kinked just off the switch toes. Difficult to manage the stress in that position. A couple of others, perhaps less significant, but again, transition to a structure. Often where we struggle to maintain ballast quality, keep the voiding away. So anything like voiding loosens the track in the ballast. A few others, Otford, fairly straightforward buckle in plain line. Norwood, again, in the S&C again, there's a sort of common theme in and around certain types of S&C. Gospel Oak, again, it seems to come up every year, Gospel Oak. I need to do a bit more work on this. It's got a checkered history for some reason at Gospel Oak. Something's not right. We need to go back and revisit what we're doing there, because it features far too many times over the last few years. Barton South was there, one at 125 mile an hour. It's on the Tamworth to Derby line. A few things on this one, and I really took a bit more time looking into this in more detail. There was a lot of movement, well, not a big buckle, 44 millimetres of movement, but flagged as a rough ride. A significant kick reported by the driver was then declared a buckle as it was on a very hot day. and then blocked the traffic initially. Several days before, we had a rough ride at this location, and looking at geometry data, it wasn't a massive amount different to this. And I think what we're starting to see, particularly in things like S&C, it's not something that jumps suddenly the track. There's often an alignment fault present there, and it's there before hot weather. The hot weather does nothing more than put a bit more force in there to get it to move quicker. We've already got a weakness in the track because it's kinked. It's going to buckle at that point because it's already misaligned. All the temperature does is wind the force up to a point where it's more likely to move much quicker. So I think some of our buckles now, where we've got to think a bit more about where the risks really are, understand particularly around behaviour around S&C, and particularly things with existing misalignment, that then suddenly gets worse, or certainly in the context of normally it's not slow moving geometry, it will get much worse when the temperatures increase in that situation. A couple of others, and one of the sort of more worrying ones here, these are plots of the number of buckles each year, and the little orange bits that don't feature very frequently are buckles where we'd already had mitigation. So where did we have a watch person? Where have we applied a speed restriction? Unfortunately, the majority of our buckles have been on sites where we've not identified the root cause, we've not picked up the deficiency, so effectively have gone unmitigated. There's a few things there. It's a worry that we've got a significant number there that weren't on there, but when you then go back and look at those buckle sites, you don't sit there and think, I can't see why it's buckled. Most of them have got a good cause. They should have been on the register when you look back with hindsight. In most cases, we perhaps have missed things there or not identified them, or it's a combination of faults. And particularly where we've got an existing misalignment, we don't perhaps take that into the standards at the moment, but couple that with shortage of ballast often around S&C, where our problems are. There's also that you can look the other way. Was this just a small number that slipped through the net? We got thousands of sites on a CRT register, which we are attempting to manage through hot weather. Potentially, yes, that's a result. How many of those would have buckled if we hadn't mitigated them? It's a good question to ask. It's not something I want to try and anger, but it's one of those where you just don't know the answer to that. We've always had those sort of controls, so it may be we're controlling most of it well. These are a small number that slipped through. Some of the other things, looking at standards and controls, how effective are they at the moment? As I said, buckle resistance, it's really about the lateral strength of the ballast and the forces, or the SFT in the rail, the forces that build up during hot weather. At the moment, our ballast deficiency, lateral resistance, whatever you want to call it, you can put different names on it. Visual inspections, cab rides, general note during supervisors' walkouts, that sort of things. How can we get better at doing something there? Can we put some technology into that? So it may not give us all the answers, but at least if it says here's the worst ones, make sure you've got all of those on the register, or here's some that are not right. You need to go and look at these in particular. So doing things there. The other thing with the track, our mitigation is only controlled by a reduction in the dynamic load. So we don't have any magic treatment that we go and put down next to the track to keep it cool or to strengthen it. We just slow trains down. So first thing we do, we put someone out to look at it. If it gets hotter still, we apply a speed restriction to it. We reduce the dynamic loading. Hopefully we reduce the risk of it buckling. And then when it gets to very high temperatures, we put a speed on where, yes, we massively reduce the dynamic loading. We're also more worried about the consequence if it does derail at 20 miles an hour. We've minimised the consequences. So it's something there. What can we do better? One of the challenges, certainly discussion at the moment, can we provide more flexible controls for different routes, for different vehicle types, making sure they can be applied operationally as well. How do you inform drivers that it's a different speed here or a different speed there, or it's a different speed with a different vehicle? At relatively short notice, it may be the afternoon where it gets hot, it gets imposed at short notice. I think some of the other things I've been looking at, making sure we've got SFT and CRT right, comes back, that's quite critical, the basis there. They're only protected if we correctly identified those and put them in a register. We don't, until it gets exceptionally hot, have something that we just apply a speed restriction because of the general condition. It relies on us recording those CRT sites and then applying mitigation there. And some of the other things, the railway's changed quite a bit. The standards, the controls, certainly they've been unchanged. We've changed some of the trigger points, but the 30 over 60, 20 and watch person, certainly for the last 30 years have been in position, and very little change there. We've made some tweaks around the limits, but railways changed a huge amount there. Amount of traffic, how do we manage that? The resources available, the access we have, the move away from red zone working. Is a watch person an effective control in a modern railway? Can we do, or can we do enough? I just went through, and I'm not going through these, but I just wrote down very quickly out of a range of standards all the things that the track engineer should do before hot weather. It's a massive list. It's huge. Compared with the resources and the funding, the access that we have available, we sort of add loads of things in the list. Oh, we got this, we'll add another one to the list. Are we really able to deliver that? We need to challenge that. What do we need to do? What can we realistically do? Because doing all of that before hot weather is pretty tough. If you look at what happens with temperature, what are we expected to manage the track up to? Is it an extreme day of 38 degrees? Is it a hot day at 35? Is it 32? You look at a quick plot there, you can see the number of sites affected. 25-degree forecast, small numbers nationally. Start ramping that up temperature, but if you go from, say, 35 to 38 degrees forecast temperatures, you've probably nearly doubled the number of sites that then suddenly come into play on the CRT register. So depending on where our expectations are, that's certainly a big change in the volume of work that could be necessary to improve that. If you look at simple one, I've just taken temperatures. Normally rail temperatures would probably peak at about 1.5 times the ambient temperature because of solar gain. What can we do affordability and performance wise? There's a few things, I think. Route strategies, making sure we know where we're heading, what's the likely impact. We've thought about that ahead of the day. We're not waiting for a discussion on the first really hot day of the year and what are we doing today. It's a bit late then. Plan that out in advance. We know where problems are likely to be. I think we need to get better at high and low risk sites. There's so much to do. We've got to work out which sites are really high risk, which ones do we really need to pay attention to. Maybe then we can reduce the number of sites that perhaps need managing. We can reduce the volumes of watch people. Some changes in the recent Mod 14, make sure we've realised those benefits. We got those in the CRT register. I think in most cases that's being done at the moment. Can we do more to avoid ratcheting? Certainly a lot of our problem. If we can't deploy a watch person, and that's quite difficult in a modern railway, we've automatically ratcheted to the next more onerous speed. So how do we avoid that? That's applying speeds that aren't needed potentially. I think some of it existing misalignments at high-risk locations that may be present before hot weather, take note of those. They're certainly, when you look at the buckle data, they're coming out too frequently in those things, particularly in high speed at the S&C. A bit more on better preparation, but I think that's going to be what do we really need to target? Can we get rid of some of the huge amount of work that we're trying to do, or focused areas better to deploy what resources we have? A few things we're trying to improve. We're still looking at, it was touched on earlier, averse replacement, a non-intrusive method of SFT we can do really quickly. It's a struggle. It's not easy, but I'm not giving up yet. Can we measure ballast profiles, adequacy, consolidation, shortages automatically? Things like watch person, we're looking at the moment, we're running some work to try and look at what we could deploy with technology to replace a watch person. Could we do more with treatment of older assets? We put a speed on a full deck timbered S&C at high speed. Could we go and strengthen it? Ballast glue the shoulders, put some lateral resistant plates, strengthen it so that we may not have the time, resources yet to renew it, but we can do something in the short term. In the longer term, yes, we've got renewal, but that's a long way before we get all of our assets to a point there, and I think weather's changing quicker than that. We've got a number of challenges coming from the Extreme Weather Task Force. Peter mentioned it earlier. I think that's something coming as these get defined and declared. We're going to have to show how we're improving some of these, address some of these questions, and some very good recommendations in there coming out. So I'm hoping that will help with some of the plan, perhaps some of the focus going forward. And in conclusion, only 20% of our buckles were previously recorded in our CRT register. Is that effective? How can we do better? One of the sites should have been on the register when revisited. Changes to track construction, specifications. We've got a generally stronger track form. Modern Sen 60 G44 sleepers, if adequately ballast, has capability to go to quite a bit higher. So we have some benefits there. We have some there, but we are a long way from having that as our predominant type of track on our main lines. We make sure we look at other disciplines. It's no use having the track fine if the OLE's causing everything to be shut. So some challenges there. Think of it as a system that we need to get through hot weather, better use of technology, definitely a focus on high risk sites. How do we get people away from having 2,500 in the database to having 100 really high risk? We know where to go. We can perhaps help people with what's actually critical. I think it was touched on earlier, by 2050, 44.5 could be common in the southeast, 37 in Western Scotland, and 40.5 in Wales. So some big challenges when that becomes the norm. And it's not just one day, that's potentially periods of time during the summer. So how long is that period affected? And I think, thank you for the invitation today. And I've taken to try and put a quote in the last slide. It's an interesting one. Jay Inslee, the Governor of Washington, we're the first generation to feel the sting of climate change. We're probably the last generation that can do something about it. So interesting words, but something to think about. That's it. Thank you.